Okay, so let's start. In the last class, we were talking about Reed-Muller codes. So Reed-Muller codes are obtained by taking polynomials as messages. So each message vector corresponds to a certain polynomial, but now it's not a polynomial in one variable, but in general in m variables. So the message polynomial looked something like this. So this would be an example of a message polynomial, and the Reed-Muller code is obtained by, or the Reed-Muller code word corresponding to a particular message polynomial is obtained by taking the evaluations of this particular polynomial at all possible points. Right? So this strictly generalizes at least the specific normalized Reed-Solomon codes. Right? And we are trying to find or at least obtain bounds on the minimum distance and the dimension of a general Reed-Muller code. Right? So first we focused on the case where R is strictly less than Q. So basically the field size is sufficiently large, and then we first showed that the dimension is less than or equal to, yeah. So the minimum, we showed that the minimum distance is at least Q minus R, right? And the dimension is R plus M choose R, right? So to prove that the dimension is equal to R plus M choose R, we formulated this as basically a counting problem, and we exactly found an expression for that counting problem. Right, for the minimum distance, again it's kind of a counting problem, but instead what we did was the following. Since the minimum Hamming weight essentially corresponds to the number of roots of any general polynomial in m variables, what we did was we picked a random point and tried to find what is the probability that the polynomial evaluates to 0 at that particular random point. And we saw that that probability is at most R over Q. Now in the last class, we also generalized this to the case where R could be greater than Q. We got a slightly more complicated looking bound. So the number of points for which any general polynomial of degree R in m variables is not equal to 0 can be lower bounded as follows. So it is greater than or equal to Q minus T whole raised to Q raised to M minus S minus. Correct? So the minimum Hamming weight is basically Q to the M minus this particular quantity. Correct? Now obtaining general bounds on the dimension when R is greater than Q is in general not very easy. But there exist some upper and lower bounds. I won't prove them over here, but I'll just state them. Right, so let KQMR essentially be the dimension of the Reed-Muller code. The Reed-Muller code with over field size Q having m variables and maximum degree equal to R. But what exactly is this equal to? So just as before, this corresponds to a counting problem, right? So this dimension is basically equal to the number of possible monomials we can construct with total degree equal to R, and each of the individual degrees less than or equal to Q minus 1. Right? So this is equal to the number of possible D1, D2 up to Dm such that each Di is an integer, Di is greater than or equal to 0 but less than or equal to q minus 1, and summation I equal to 1 to m di is less than or equal to r. It's a simple looking counting problem, but again we can't get a closed form expression, but we can prove the following upper and lower bound. K q m r is less than or equal to this k plus q m r and is greater than or equal to k minus q m r, where k minus q m r is equal to complicated looking expression. So it is a max of q to the m by 2 to the m minus k plus q m q minus m q minus 1 into m times. And this is if r is greater than or equal to q minus 1 by 2, that is equal to the maximum of m choose r floor of r m full raised otherwise. So this is a lower bound. A plus mr is basically equal to m choose r. But it's equal to the minimum m. So there's no one single regime where this bound is either bound is always tight. So we've seen that at least when r is strictly smaller than q, we know that kqmr is exactly equal to m plus r choose r. We derived that in a previous class. But if q is strictly smaller than r or less than or equal to r, then you only have these upper and lower. If you're interested in the proof, you can take a look at the textbook, which is Essential Coding Theory by Guruswami, Rudra, and Madhusudan. But in general, we can prove these upper and lower. So it's not an easy problem to get a closed form expression, right? Now let's see what happens to this when the field size is binary. Okay, what is the minimum distance and what is q equal to 2? How good are Reed-Muller codes in general, right? So what do we know about the minimum distance? You know that the minimum distance is greater than or equal to q to the power m. So in the last class we derived a bound, right, which was q to the m q minus t times q to the m minus s minus 1, correct? And in this case, what are t and s? So q is equal to 2, correct? So if we take let's say a polynomial of degree r, right? What are S and T? Q is equal to 2, so Q minus 1 is equal to 1, correct? And T should be strictly less than Q minus 1, less than or equal to Q minus 2, strictly less than Q minus 1. So the only choice is T should be equal to 0, right? Or S is equal to R, right? So this quantity will be Q times Q raised to M minus R minus 1, or Q raised to M minus R. So this is equal to Q to the M minus Q raised to M minus R, which is Q to the M into 1 minus Q to the minus R. Sorry, wait, let me see if I got this. Is not equal to 0. So it's not Q to the M minus this, it is just equal to this. So the number of A f of A is not equal to 0. So this is greater than or equal to Q to the M minus R. Equal to the M. Okay, but what is Q to the M equal to? Or let me put it in a slightly different way. What is N equal to? N equal to Q power M, right? So this is equal to N into Q to the power minus R. Right? Okay, so suppose that we want an asymptotic distance which grows like n times delta, okay? Some small delta. So this implies that I should take 2 to the power minus R to be equal to delta, or R should be log 1 over. You agree? Okay. Now that's fine. What about the dimension? Can we give some guarantees about the dimension? So we know that this is at least, the dimension is at least k minus qmr. So in this case, is r greater than or equal to q minus 1 times m by 2? Yeah. Sorry? Correct. Correct. So what would, so how would you choose? So you want r to be equal to log 1 over delta, right? And delta is typically a constant. So you want to aim for constant minimum distance, right? Or constant fractional minimum distance. So r is that. So what can you say about m in that case? How should it grow with? Should it grow with n, or is it a constant? Right now we're interested in the regime where n tends to infinity. Okay, n is very large. So r is something which is a constant, right? And n is roughly 2 to the n. So m should grow with n. Right? M grows as log n. So in this case, m is significantly larger than, right? Okay. So the bounds were the following: if r is larger than some constant times m, then we can use this particular bound. But r is not much larger than m, so we should be using this particular bound. Q is greater than or equal to, correct. But k is greater than or equal to k minus, right? So right now I'm just interested in a lower bound. I want to know what can be achieved, right? So out of these two, which one do you think is going to be larger? You think this is going to be larger, and why do you think that is the case? Since, correct, correct. But then remember, so this is of the form 1 plus constant divided by m whole raised to the m. Right? So if you look at this particular term, this is essentially, this is roughly 1 plus 2r by m, ignoring the flow, whole raised to the m. Correct? Or this is equal to 1 plus r by m whole raised to m by 2r whole raised to 2r. Okay. As m tends to infinity, what does this tend to? Yeah, e, right? So that's a constant. So it's constant raised to 2r, right? So this is roughly e to the 2r. And what about this particular term? M choose r. Yes. Sorry? Hint. So how do you think this would grow? Do you think this is an increasing? So this as we've seen is, at least for m being very much larger than r, this quantity does not grow much with m. What about this quantity? Will it grow with m? How fast do you think it will grow with m? Correct. MC, m choose r. Okay, sure. Okay. Which one would be smaller? So m choose r. Okay. So what is this equal to? Yeah, m choose m minus r, but m into m minus 1 up to 1 whole divided by r into r. Correct? Because m tends to infinity, what happens? So maybe let's perhaps look at this a little more carefully. Maybe I should have done it in a slightly different way. Uh, but fine. So what we want is, so how do we hope that the dimension with scale with n. So let's work around it in the following way. Suppose I want m. So we want k mr to be greater than or equal to n times r for some constant r. Okay. So again, so certainly kqmr we know is greater than or equal to m choose r. It's greater than or equal to the maximum of these two, right? And therefore is greater than or equal to m choose r. Now, how do I want this to grow? I want this to grow as 2 to the something times n. Right? So I want this, but what is n equal to? That's simple. Yeah, it's 2 to the power n. Right? So I want this to be approximately close to 2 to the power, right? Or 2 to the n, 2 to the m times r. Right? And when can I get that? I can get it only if r is very close to m over 2. Why is that true? So m choose r is less than or equal to me by r whole raised to the r, but a better bound for m choose r. So when r is some constant times m, this is exponentially growing in m. Okay? But m choose r is also equal to, by Stirling's approximation, is approximately equal to 2 raised to m times the binary entropy of r by m. Right? And I want this to be approximately equal to 2 to the power m. We want this to be approximately what it should be to the m times r. Right? So what does that tell us about h2 of r by m? Yeah, log r to the base 2. Are you sure? So let's take log on both sides. The left hand side is going to be m times h2 of r by m is equal to m plus log r to base, right? So h2 of r by m is going to be 1 plus log r base 2 divided by where, remember that r is something strictly less than 1, right? So this quantity is going to be slightly less than 1. As m tends to infinity, this term is going to tend to 0. So r by m is going to be very close to half, going to be equal to some half minus some delta. Okay, where this delta is something tending to 0 at a certain rate. Okay, so what does that tell us about the minimum distance? Yeah, any questions? Capital R is the rate that we're targeting. Yes. Yeah, it's binary, right? It's 1 bit per dimension, right? So in n channel uses, you're transmitting fewer than, you can't transmit more than n bits, right? Anyhow, so it has to be fewer than n bits. So you're transmitting nr bits in n channel uses, right? Which per dimension, it's less than 1 bit per dimension. So in one channel use, the amount of information that you're giving is r bits, where r is strictly less than 1. Okay, and what did we say of the minimum distance? This is greater than or equal to 2 to the m minus r. R by m. Right? So what kind of a minimum distance does this guarantee? So it is 2 raised to m into m times delta. Half plus. Right? So for constant rates, this doesn't quite give us linear minimum distances. What delta is something which is very small, right? It's because, so we want this, right? We know that h2 of r by m is equal to 1 plus log r by m. As m tends to infinity, this quantity tends to 0, correct? And that happens when r tends to half, right? Or r by m tends to half, right? So r by m is something which approaches half as m tends to infinity. So again, if I plug that over here, then I get half minus delta. So it is, so this is 2 raised to m into half plus delta. So this particular bound, but what is, so this is 2 raised to m delta. So remember that delta is something very close to 0 times 2 raised to m by 2, right? So this is approximate, this is very close to 2 raised to m by 2, or square root of 2 to the power m, which is root m. So it's still possible to get constant rate and large minimum distance, but it doesn't get us all the way up to, say, linear minimum distance. These bounds are not good. Okay, so now we've seen two classes of algebraic codes, right? One was the class of Reed-Solomon codes, the other was Reed-Muller codes. Yeah, no, we started with dimension and then we ended with the minimum distance, right? So dimension equal to n times r implies that the minimum distance should be approximately equal to this. Okay, so now we've seen two classes of codes, right? The first was the Reed-Solomon codes and then the Reed-Muller codes. The nice thing about Reed-Muller codes is that you can construct them over smaller finite fields. But Reed-Solomon codes are somehow more widely used in practice because they can be constructed over, although they can be constructed only over large fields. So then what is really the utility of a Reed-Solomon code? It can be used in some applications at all. So one useful property of a Reed-Solomon code is that they can be decoded very, very efficiently. So there exists a decoder for any generalized Reed-Solomon code that has order n square complexity. Right? So it decodes all the way up to half the minimum distance and it operates in just order n square time. In fact, this has been improved upon. You can bring it down to order n times polynomial in log n. But for now, let's assume that this is true. Okay. The question is, can this be used to design a more practical? So the problem with this is that you can only construct it over large field size. So if you want codes of very, very large block lengths, then obviously you can't use a Reed-Solomon code because you have to use a very large field size. Right? So then what do we do? Now, if you recall from the channel coding class, there is a way of, if you take a random code and then use it over any discrete memoryless channel, this random code can achieve capacity. But the only problem is you have to do whatever maximum likelihood decoding, which takes exponential time. So let us consider any discrete memoryless channel. Right? For example, let us take the binary symmetric. although it doesn't necessarily have to be just the binary symmetry. It could be any TMC. Okay. So from the channel coding theorem, there exist codes of block length n for n suitably large, rate close to capacity of that particular discrete memoryless channel, and achieving a probability of error being less than or equal to some alpha raised to the power 10, right? Or if you want to this way, less than or equal to 2 to the minus alpha times n for some constant alpha. So you can achieve exponentially decaying probability of error, but for any block length n, rate approximately equal to c. But the only catch is that the decoding complexity is exponentially is 2 to the power. In fact, it's 2 to the n times c, because you need to, if you're doing something like minimum distance decoding, then you have to find the distance to each and every code word, which is roughly 2 to the n. Correct? So now, is it possible to design a code which gives you roughly the same things? It has to be of block length n, for n being very, very large. The rate should be close to capacity. The probability of error is small. I don't really care how fast it decays with n, but as long as it decays with n, I'm fine. But the decoding complexity should be just polynomial in n. Is it possible to ever design such a? It turns out that Reed-Solomon codes can help us do this, right? And that's achieved using this very nice technique called code concatenation. Okay? So let's think about what we have now. So for any block length, let's suppose I take a very short block length code. Okay? One of these codes. Okay, one of these good codes. This code achieves a small probability of error but has high decoding complexity. Right? So if I take a very short block length code, then the decoding complexity is manageable. But now the probability of error could be something large. So what can I do? I have these n symbols, right? My goal is to design a code for n channel uses, right? So let me do the following. I'll first start with this initial approach where I split the n channel uses into sub intervals, okay, or sub blocks. My code word is going to compose of several sub blocks. Okay, so n is very large. I'll split them into sub blocks of maybe n prime channel uses each. Okay, I'll use I know how to construct good codes with large decoding complexity, correct? So in each of these blocks, I'll use this particular code. Okay. So we choose a good code, in the sense capacity achieving code, of block length n prime. N prime is going to be much smaller than n. Okay, so think of it as something like order log n. So it has block length n prime and rate close to capacity. So rate is close to capacity of the channel. Right? So what can we guarantee? So if you look at any sub block, it is going to achieve a probability of error that is exponential in n prime. Right? And the decoding complexity is also going to be exponential in n prime. So each subblock is 2 to the constant times n prime, right? So 2 to the c times prime, right? And if I choose my n prime to be, if n prime is order log n, in particular, I'll choose this n prime so that this particular decoding complexity, the decoding complexity is just n square. Yeah, I'll choose the constants carefully enough so that the overall decoding complexity turns out to be n square. Okay, this is whatever the decoding complexity of each particular block. Okay? Fine, whatever. Let's take that this is some polynomial. So now if I have to decode all of these, what is the total complexity? It is equal to the number of blocks times the complexity of decoding each block. So total decoding complexity equal to n by n prime times n square, which is still polynomial in whatever at most n cube, right? Because n prime is something like logarithmic in n. So this is n cube divided by logarithmic in n, which is at most n cube. Okay? I'm not going to be very careful with my choice of parameters and stuff. My goal is to just get polynomial decoding complexity. At most maybe n cube decoding complexity. Okay? Everything is fine so far? Great. So now, excellent. So now I've somehow magically reduced the decoding complexity, but I'm paying a price. And the price is the probability of error. Right? Now, obviously, the probability of decoding each block, the probability of error of decoding one particular block is exponential in n, right? It's 2 to the minus some alpha times n prime, right? So the probability that the ith so the probability that ith block is decoded incorrectly is less than or equal to 2 to the negative alpha times n prime, right? But n prime is growing logarithmically in n, so this is polynomial in 1 over n, whatever. So this is less than or equal to 1 by n raised to beta for some constant beta. Correct? Now, okay, so this is the probability that one particular block is decoded incorrect. In particular, this n raised to beta could be so beta could potentially be smaller than 1. Is some positive constant. Okay. Now, when do we say that decoding is actually successful? It's successful only if all the blocks are decoded correctly. Correct? Now, if I want a small enough complexity, then I have to pay a price in terms of the probability of error. Correct? It's possible that so the probability that all blocks are decoded correctly is 1 minus the probability that any block decoded incorrectly, which is greater than or equal to 1 minus n times, there are, or n by n prime times 1 by n raised to beta. So this is fine, but now it may be possible for me to choose my n prime carefully enough so that this overall quantity is still decaying in n. But that means that this complexity might go up a little bit more. But can I do it even without all of this? Is it possible to actually achieve a very small probability of decoding error? Okay. Sorry? Correct. In particular, can I even get an exponentially decaying probability of error? The probability of error of one particular chunk or one particular block is small. But the problem now is that I have too many blocks, which may be a lot. So this is where Reed-Solomon codes all of a sudden are helpful. So I'll do the following. Now out of these, so I have these chunks, right? How many of them can be in error? The probability that one particular chunk is in error is whatever 1 by n raised to beta. Right? So in expectation, how many of the chunks are going to be in error? You have n by n prime chunks. The probability that one chunk is in error is 1 over n raised to beta. So on average, how many of them are going to be in error? Y. Sorry, what is P? Correct. So it's not n, but n by n prime, because this is the number of chunks times the probability of error of one particular chunk, which is 1 by n raised to beta. Right? Okay. Now, what is the probability that, say, significant? So this is the expected number of erroneous chunks. What is the probability that the number of erroneous chunks is greater than or equal to, let us say, some delta times n, or delta times n over n? Yeah. Okay, but there are better inequalities. Okay. So, for example, if I use a Chernoff bound, then I get a bound which is exponential in n or n by n. So if I use the Chernoff bound, this is less than or equal to 2 raised to minus some constant, call it gamma, times n over n prime. Right? Okay, very good. So this is so now, but this is the probability. Okay, so this is the probability that the number of chunks in error is greater than or equal to this. Right? This is only if I use this good code for encoding and decoding each particular chunk. Correct? So it would work the following way. So you have the message. So think of the following. You have the following message, and the message, the k-bit message, is split into chunks of k by n prime size each. So the k-bit message is split into chunks of size k by sorry, kn prime by n each. The total number of chunks is n over n prime. So I'm splitting the k-bit message into chunks of size kn prime by n each. And and suppose that I encode each of these using the capacity achieving code of block length n prime. Right? So this is what I started off with. Now what I know is that if I use such a scheme, then some of these chunks could be in error, but not too many of them. Right? The number of erroneous chunks is going to be at most delta times n by n. Okay? For where this delta is like very small, it's close to zero. It's approaching zero as n tends to infinity. Agree with me so far? So the protocol is clear, right? This was the protocol that we had. Now, if there were some way to maybe correct these errors, then I would ensure that all of the chunks could be decoded error-free, right? As long as this code does not make more than these many errors, right? For example, suppose that I used a minimum distance decoder, a good error correcting code with minimum distance at least twice this particular amount, right? Then as long as this particular stage made not more than these many errors, everything will be decoded correctly. All the message bits would be decoded correctly. Okay? So let us look at the following architecture. I have the message bits. Which consists of k bits, right? What I will do is I will encode them using a Reed-Solomon code, okay, of a certain block. Okay? So a Reed-Solomon code over a field size, say fq to the power, okay, let me call it L. But this L could be something very large. Let's take q equal to 2 just for simplicity. So it's f2 to the power L. Field size has 2 to the power L, where I'll let L to grow with n. Okay? And this has minimum distance, which is larger than, say, 2 times delta n by n. Okay? Now this Reed-Solomon code consists of symbols. Okay? How many symbols are going to be there? The number of symbols is going to be, so the block length, so this is the minimum distance. I'm going to choose the block length to be equal to n times c divided by from 2 to the power n. Right? Roughly n times c 2 to the power. Okay. So I want a minimum distance which is approximately equal to this, but delta is something which kind of shrinks as n tends to infinity. So really the minimum distance is tending to 0 as n tends to infinity. Tends to 0 as n tends to infinity. So the rate of this particular Reed-Solomon code, I can choose it so that the rate tends to 1 as n tends to infinity. So this Reed-Solomon code can correct as long as, so you can view this particular sequence as a sequence of blocks or of 2 to the L bits each, right? So this is actually the field size. So you can view these code words n double prime. So let's say that the block length is equal to n double prime. So the code word corresponding to this, so the Reed-Solomon code word, right? So it consists of n double prime symbols, and each symbol belongs to f2 to the power n, right? Because I've used the Reed-Solomon code of over field size f, over field size 2 to the power n. Correct? Okay, so far. Now I can view this as elements of the finite field, but I can also view them as bits, right? As L bits of L bits over the binary. Which one? As this? So we'll see in a little bit. Right? So ultimately, I want to make sure that K is equal to n times C. C as the capacity of the DMC. Right? So really, I should be taking this as not NC by 2 to the L, it should be NC by L. So I can view each of these CIs. So CI is in F2 to the L, but I can also view them as binary strings of length L. Correct? And then what do? I'll encode each of these messages or each of these code symbols or each of these blocks independently using a capacity achieving code. Okay. So that the overall block length is now equal to n. So this code, this capacity achieving code is of a short block length. It has a very small probability of error and it has rate close to capacity. Now I've designed a two-stage coding scheme wherein I first encode the message using a rate almost close to 1 Reed-Solomon code, and then encode each block using this capacity achieving code. What guarantees do I get? So firstly, the overall probability of error is decays now exponentially in n. You agree because of this, right? Because the number of blocks in error is at most delta times n. So the probability that the number of errors is greater than delta times n is decays exponentially in n. And all of these errors, as long as the number of errors is less than this, number of erroneous chunks is less than this, the Reed-Solomon code is definitely going to correct it. Right? So overall probability of error is less than or equal to the probability that greater than whatever delta times n by n prime chunks are in error, because as long as fewer chunks are in error, the Reed-Solomon code is going to correct. But then the probability of this happening is 2 to the minus delta n over n. Right? So the probability of error is decays exponentially in n. What is the rate? Now, the rate is basically the rate of this times the rate of this. Right? Because I originally have k symbols. I'm converting this to some k prime symbols using this code where k over k prime is close to something. So we achieve the singleton bound. So it is 1 minus delta n over n prime. One over n minus delta n. So what is the rate? Rate is equal to k divided by n, which I can write as k divided by k prime into k prime divided by n. But what is k over k prime? It is the rate of the Reed-Solomon code. Correct? And what is the rate of the Reed-Solomon code equal to? Yeah, it's close to 1, right? So if you use the singleton bound, then the dimension is equal to n minus d plus 1. Right? So it is n minus d plus 1, or in this case, the block length is equal to k prime by k prime times k prime by n. So this is roughly 1 minus delta. But what is k prime by n? That is the rate of the capacity achieving code, which is close to c. So from a short block length code, achieving an exponentially decaying probability of error over that particular block length, we've constructed a code over a much larger block length, which still achieves an exponentially decaying probability of error. The rate is still roughly the same, and the decoding complexity is now much smaller. Right? The decoding this capacity achieving code is still polynomial in n, as long as n prime is chosen small enough. And decoding the Reed-Solomon code is also efficient, just quadratic in it. Right? So this gives you overall the probability of error is exponential in n. The decoding complexity is polynomial. And what is the rate? The rate is close to capacity. This approach where you take a short block length code, you convert it to a large block length code using this two-stage encoding and decoding technique. This is something called concatenation, code concatenation. It was originally proposed by George Forney, and it was used in a slightly different approach for a slightly different problem. In fact, you can take any code and convert it to a better code for a larger block length using this particular approach. Right. So this shows that, at least in principle, theoretically, it is possible to design codes which have polynomial decoding complexity, rates approaching capacity, and probability of error which decay exponentially in it. But again, they're far from being actually practical. At least on paper, it is polynomial, but in practice, this turns out to be much larger. For example, even order n cube for practical purposes is too large. In fact, if you want to implement something on chip, anything larger than order n log n or order n log square n is considered to be too expensive. So in the next few classes, we'll discuss a new class of codes called the low density parity check codes, which in fact have much lower decoding complexity. We'll see that the decoding complexity is just order n log n, roughly. They achieve capacity of a large class of discrete memoryless channels, and they have very low probability of error. So those are implemented in practice. So many of the modern chips, in fact, do have low density parity check codes run. Even our phone, for example, for Wi-Fi and so on, they use LDPC codes. Like the 5G standards, for 5G standards, even voice and data will use LDPC code. All data channels will use LDPC. Right? Any questions? Okay, so let's stop here.